In probability, one of the big areas of questioning is theory questions where there is no context, and we've got one here. So with a question like this, the best way to get started is to either set up a Venn diagram or a probability table or Carnot map, which is what we're doing in this case. So if the probability of A is equal to 0.6, that means the column for A must total to 0.6. And if the probability of B is 0.75, that means the row for B must total to 0.75. Now, that tells us that we can fill in the missing bits here. So if A is 0.6, not in A is 0.4, and if B is 0.25, not in B is 0.25. So what else do we have? Well, we know that the intersection, so this first cell up here in the top left, is 0.42. So we can fill in the missing bits now. Everything should fill in. So from 42 to 60 is 18. And we know from 18 to 25 is 07. And this one must be 33. So I've just done some decimals work to fill in those missing cells. And now we're looking for the probability of not in A intersecting with not in B. So that is this cell just here. So we can answer the question. We say that the probability is 0.07. Now, one of the important rules to remember for probability, for theory questions in particular, is this boxed rule here that the probability of the union of A and B is equal to the probabilities of A and B together, but we don't want that overlap being counted twice, so we subtract the probability in the intersection. And when we look at our Carnot map, we can see that those three cells there are the probability of A or B. So that means the intersection is only included once. So that is a really important rule to be able to apply in a probability question. So when we look at the next example, they're giving us some information about the union and the probabilities of A and B, and they're asking us to find the intersection. So that's a straightforward substitution into that rule. We therefore know that the probability of the union is equal to the probability of A plus the probability of B minus the probability of the intersection, which is what we're trying to find. So we can see that if the probability of A and B is 1.1, we've got way too much here because together they only equal 0.9, so we've got an overlap of 0.2. Therefore, the probability of A intersection B is equal to 0.2. Students often get independent and mutually exclusive events confused, and it's very, very important that you can keep them separate. When we talk about independent events, we're talking about situations where the first time you do something, it doesn't have any impact on the probability of that event occurring the next time you do it. So for example, tossing a coin, if the probability of tossing a head is a half, it's not going to change no matter how many times you toss that coin. Same with when you're rolling a die, shots on goal, anything that you're repeating, and by doing it more and more, it doesn't change the probability. That makes it an independent event. So there's a very, very important little formula to remember for independent events. And when you see that rule there, that the probability of the intersection between A and B is equal to the probability of A times the probability of B, you have to remember that that rule is relevant for independent events. So in those contexts where the probability does not change each time you perform the experiment. So in this instance here in example 1, we're told that the events are independent and we're asked to find the probability of A union B. So we lock in on the word independent, and when we see that word independent, or we have a situation where events are independent, we know we have to use this rule here. So I'm just going to write that rule down, and then we're going to see what we have and what we need to be able to answer the question. So in the question, they've given us the probability of A, and they've also given us the probability of B. All right, so with that, we therefore can determine that the probability of the intersection is equal to 0.2 times 0.5. So when you're multiplying decimals, just multiply the numbers. So 2 times 5 is 10. And there were 2 decimal places in the question. Therefore, there must be 2 decimal places in the answer. So the probability of the intersection is just 0.1. Now, they were asking us to find the probability of A union B. Well, now we need to think of a rule or a formula or an equation that connects A union B with that information we have. And that's the rule, the addition rule that we used a minute ago, that the probability of the union is equal to the probability of A plus the probability of B minus the probability of the intersection. So subbing in what we know that A was 0.2, B was 0.5, and we found that the intersection was 0.1. So we can see that it's 0.7 minus 0.1 is 0.6. Now, mutually exclusive events mean that the probability of the two things cannot happen simultaneously, or in other words, there's no intersection. And I think the best way, well, I find this the easiest way to remember just what it means for events to be mutually exclusive, and that's to have a Venn diagram where there is no overlap. So the Venn diagram makes it really crystal clear that the intersection is equal to 0. There is no intersection. And if I were to do a Carnot map, A not in A, B not in B, I would know that I need to put a 0 in that first cell because that's the intersection cell, the A intersection B. So when events are mutually exclusive, we know that the probability of A intersection B is equal to 0. So you must make sure that you keep those two rules separate because they're quite similar. Where's that other one gone? Okay, so the probability of A intersection B for independent events is equal to probability of A times probability of B. But when the events are mutually exclusive, the probability of the intersection is equal to 0. So here's an example of where we're told that the events are mutually exclusive. So, you would be visualizing that situation where the two cells, the two circles in your Venn diagram are separate. So mutually exclusive, lock in on that, and we know straight away, mutually exclusive means that there is no intersection, that the probability of A intersection B is equal to 0. Now, they've given us some information. They've given us the probability of A and the probability of B, and they've asked us to find the probability of the union. So we need a rule that connects those different probabilities, and so it comes back to that probability of A union B. So that's the only rule that we have that has A union B in it, which is equal to the probability of A plus the probability of B minus the probability of the intersection. And we know that A is equal to 0.3, the probability of B is 0.45, and because the events were mutually exclusive, the intersection, or the probability of the intersection, is 0, so we can quickly determine that the probability of A union B is equal to 0.75.